All right, so previously I just solved for the load voltage and the load current that we expect to see with the load connected. Now we're going to get into the actual process of Thevenin and Norton, which we know the first step is to remove the load resistor from the circuit. So let's go ahead and let me take this circuit without the load resistance, and I'll copy that into the next slide. I'll go ahead and put it here, and so we know that we don't have the load resistor in, but what we want to solve for is the voltage, the open circuit voltage here without the load, okay? So what's interesting is that we can very easily solve for this open circuit voltage because, again, this current is going to be 0 because there's nothing here. So no current can flow through this resistor because there's nowhere for it to flow. It's not able to flow through this gap, okay? So no current there basically means all I'm left with is this voltage divider right here. And so I just need to find this node voltage here, and then I know that my voltage drop across the 3K is 0 because the current flowing through it is 0. So once I find this voltage, I know this voltage, and I know this is 0, so I can find my open circuit voltage quite easily. So let's just go ahead and say that let's call this V int. Nope, let's just call it Vx. I always call it Vx. I'm just going to do it again. Vx is equal to 9 volts multiplied by 2K divided by 1K plus 2K, which is 3K, or 2/3 of 9 volts, which gives me 6 volts. Okay, so that's going to be my Vx, which, again, I have no drop across my 3K, gives me 6 volts here. So my open circuit voltage, which is my Thevenin voltage, is 6 volts. Okay, so I found my Thevenin voltage. And so if I'm trying to build up my Thevenin equivalent, let's do that on the next slide. Put my Thevenin equivalent right here. I know I have a Thevenin voltage and I have a Thevenin resistance. And then I'm going to put my load in at the end and determine whether or not I did this right. I just found my Thevenin voltage. That was 6 volts. So let's go ahead and write 6 volts right here. Okay? The next thing I'm going to do here, let me draw my Norton circuit as well. Sorry, my Norton resistor goes in parallel. And then my load would go here. And I'll just go ahead and ground this. And this is I Norton and R Norton. So let's go back. And now let's solve for the Norton current. Okay? So what we're going to do is, so the first step was find the Thevenin voltage using circuit methods to determine VOC. We need to now find the short circuit current, which is the current through the load when the terminals are shorted. All right, so we go here. Nope, I went too far. We go here. We draw a short here. Let me actually just go ahead and take this circuit. Okay, and we are interested in determining, so now there's not an open there, there's actually a short. I'm going to short these. And I want to know what is the current that flows in that short. That's my short circuit current. Okay, so what I can do is I can notice now that since I have a short there, I have a 2K and a 3K that are in parallel with one another. They share this node, they share this node. They've got Vx on one side and ground on the other, so those are in parallel. And I can find the equivalent, which would just look like this, just be a voltage divider, where this is 1K, this is 9 volts, and then my equivalent is 2K times 3K divided by 2K plus 3K, or 1.2K here. And so I can determine this voltage very easily using a voltage divider. 9 volts times 1.2K divided by 2.2K. That gives me, let's see, 9 times 1.2 divided by 2.2, 4.91 volts. Okay, now that I know that this Vx is 4.91 volts, I can determine the short circuit current very easily because I know this is 0, right? My entire node here, this ground node, is at 0 now that I have a short there. So I can very easily determine the current I short circuit by saying I short circuit is the voltage drop cross my 3K resistor, 4.91 minus 0 divided by the resistance, and that's going to give me 1.63 milliamps for my short circuit current. All right, so I've got my short circuit current, and now what I would do is I would come right over here, and that would be my Norton current. So that's going to be 1.63 milliamps, okay? All that's left now is to find my R Thevenin and my R Norton. I'm kind of running out of time. Not running out of time, but I'm running out of space on this slide. And this video is getting a little bit long, so in the next video, I will go ahead and determine that resistance, and then we can check our load to make sure that we are getting the value that we expect from the first slide, which is 1.28 volts and 1.28 milliamps. All right, go ahead and end this video now.